welcome to another module in this massive open online course. So, let us continue our discussion on linear time invariant systems and what happens when a signal xt is input to a linear time invariant system. So, consider a signal xt input to an LTI, that is your linear time invariant system. Remember, yesterday we elaborated on the properties of a linear time invariant system, that is linearity and time invariance. So, let us consider a signal xt that is given as input to a linear time invariant system. Okay. So, we have our LTI system. Okay. So, xt and let the corresponding input output be yt. So, this is our LTI system. So, yt is the output of the LTI system, xt is the input to the LTI system, correct, and any LTI system is characterized by an impulse response ht. That what is the impulse response ht? That if the impulse, that is your Dirac delta function delta t, is given as input to the LTI system, the output is represented by ht, which is the impulse, which is the response to the Dirac delta function delta t, and this is known as the impulse response of the LTI system, and this fundamentally characterizes the properties and the behavior of the LTI system. And the output corresponding to any signal, any input signal xt, can be described in terms of the input xt and the impulse response ht of the LTI system as follows: yt, that is the output corresponding to any signal xt, is xt convolved with ht, where xt is your input signal. This is the convolution operator. Yt is xt convolved with ht. Therefore, if I know the impulse response ht of the LTI system, that completely characterizes the LTI system. For any given in other arbitrary input signal xt, the output yt can be derived by convolving the input xt with the impulse response ht, and this convolution operation is represented as, this is equal to basically integral minus infinity to infinity x t minus tau, or that is your x tau h t minus tau d tau, which is also equal to integral minus infinity to infinity x t minus tau h tau d tau. So, the output yt is the input xt convolved with the impulse response ht, and this has a very interesting, the convolution has a very interesting convolution follows a very interesting property. If I consider the Fourier transform of the input and the output, let xt have a Fourier transform, or xt be a Fourier transform pair with xf, the output yt be Fourier transform pair with yf, that is Fourier transform of yt is given by yf. The Fourier transform of the impulse response ht be given by h of f. Then we have in the time domain yt equals xt convolved with ht. This implies in the frequency domain the Fourier transform yf equals the input Fourier transform xf times, that is the product hf, that is convolution in the time domain becomes multiplication in the frequency domain. This becomes multiplication. This is a convolution satisfies a very interesting property, that is if two signals are convolved in the time domain, that is yt is a convolution of xt with ht, then the Fourier transform of yt, that is yf, is obtained by the multiplication of the Fourier transform, that is the Fourier transform of xt, that is xf, with the Fourier transform of ht, that is hf. So, yf equals xf times hf, that is convolution in the time domain is multiplication, is equivalent to multiplication of the two signals in the of the Fourier transforms of the two respective signals in the frequency. And this is one of the fundamental properties of linear systems, and it is also very applicable. It is one of the fundamental principles of communication, because we are going to look at several instances where an input signal is passed through an LTI system and we derive an output signal, and therefore it is very important to remember that the Fourier transform, right, or the spectrum of the output signal is derived by the multiplication of the spectra or the Fourier transforms of the input signal and the impulse response. All right. Now, let us look at another concept, that is the cross correlation between two signals. So, we will start looking at another concept, that is the cross correlation. The cross, so consider for this purpose, consider two signals xt and yt. Or two signals x1t comma x2t, correct. The cross correlation function r1 to t the cross correlation function r1 to tau is defined as, well, r1 to tau equals integral minus infinity to infinity x1t x2 conjugate t minus tau dt, x1t x2 conjugate t minus tau dt. This is r1 to tau, this is the autocorrelation. For a lag tau, that is what we are doing, is we are taking x1t, multiplying it by the shifted version of x2, that is x2 conjugate t minus tau, multiplying x1t by x2 conjugate t minus tau and integrating from minus infinity to infinity. This basically this is a measure of the extent of similarity between x1t and x2t for the lag tau. So, this characterizes, it is important to know the meaning of the autocorrelation, characterizes the extent or degree of similarity between x1t comma x2t for a lag or shift of tau, for a shift the extent of similarity between x1t and x2t for a shift of tau, that is corresponding to the shift of tau. What is the extent of similarity between this signal x1t and x2t minus tau? Alright. Now, simplify this, that is we have R1 tau or R12 tau, we have written this as x1t minus infinity to infinity x1t, x2 conjugate t minus tau. I am going to write this as x2 conjugate minus tau minus t dt. Now, let us define x2 tilde t as x2 of minus t. This implies x2 conjugate x2 tilde of tau minus t equals x2 of t minus tau. This implies x2 conjugate of tau minus t equals x2 conjugate of t minus tau. Therefore, here instead of x2 conjugate t minus tau, I can substitute, here I can substitute x2 tilde of tau minus t. So, therefore, this becomes, the cross correlation becomes, this is integral minus infinity to infinity x1t x2 conjugate tau minus t dt, and notice this is nothing but convolution of x1t and x2 conjugate of t. This is basically, you will see, realize that from our definition, this is convolution of, it follows from the definition of convolution that this is the convolution of x1t with x2 conjugate of t, but realize x2 conjugate, that is x2 tilde, I am sorry, this is x2 tilde conjugate tau minus t. This is a convolution of x1t with x2 tilde conjugate t, but x2 tilde conjugate t is equal to x2 conjugate minus t. So, this is the convolution of x1t with x2 of minus t. Okay. So, R12, or you can also replace this by tau, that is R12, or you can also replace this by tau, since t here is the variable of integration. So, this is tau, this is tau, this is minus tau. So, I have R12 of tau equals x1 tau convolved with x2 conjugate of, this is x1 tau convolved with x2 conjugate of minus tau. Remember, this is the autocorrelation of x1t and x2t corresponding to a lag of tau. This is the autocorrelation function of x1t. Two different signals x1t and x2t correspond to a lag of tau. We have shown that this is basically the convolution between x1 tau and x2 conjugate of minus tau. There is convolution between x1 and the conjugate version of x2, there is conjugate x2 and flip it, x2 of minus tau, x2 conjugate of minus tau is nothing but flip it about the origin and take the complex conjugate, alright. And this autocorrelation is an important measure because it is a measure of the degree of similarity between x1 and x2 for a lag of tau, alright. And this has a lot of uses, as we are going to see later in our study of communication system. This measure of this measure, that is the autocorrelation between two different signals x1t and x2t. Okay. Now let us try to look at this in the frequency domain. Naturally, convolution in the time is, that is convolution in the tau domain. Of course, now this is not even time, this is tau. Remember, this is the lag or shift. Now, if we take the Fourier transform of this, that is denote this by S12 of f equals integral minus infinity to infinity R12 of tau e to the power of minus j 2 pi f tau d tau, then we know that this convolution in the tau domain is multiplication in the frequency domain. Therefore, we can write from the property of linear systems or from the property of convolution S1 to f is x1f times the Fourier transform of x2 tilde or x2 conjugate, Fourier transform of x2 conjugate minus t. Now, what we have to do is we have to derive the Fourier transform of f2 conjugate minus t. That is, what is the Fourier transform of f2 conjugate minus t. Now, we know that if x2t forms a Fourier transform pair with x2f, then x2t is given by the inverse Fourier transform, that is x2f e to the power of j 2 pi f t df. Consider the conjugate of this. Well, if I replace this by minus t, this becomes over here, this becomes minus t, and now if I consider the conjugate, correct. Now, if I can, for instance, let us look at this rather than the inverse Fourier transform, let us look at the Fourier transform, that is x2 of f equals minus infinity to infinity x2 of t e to the power of minus j 2 pi f t, correct. Now, if I replace dt, correct. Now, if I replace t by minus t, so let us now replace, or let us say t tilde equals minus t, then what we have is dt tilde equals minus dt. So, this integral becomes t tilde equals minus t. So, this integral becomes infinity to minus infinity x2 of minus t tilde e to the power of j 2 pi f t tilde minus d tilde. I can remove this minus sign by interchanging the order of integration. So, this is, if I flip, instead of infinity to minus infinity equals minus infinity to infinity. Therefore, x2 of minus t tilde e to the power of j 2 pi f t tilde, the minus sign in d tilde goes because I change the order of integration. Now, if we consider the complex conjugate, now consider complex conjugate if we consider the complex conjugate of x2 f, I have x2 conjugate of f equals minus infinity to infinity x2 conjugate of minus t tilde e to the power of minus j 2 pi f t tilde d tilde. And therefore, now what you can see from this, is that the Fourier transform of x2 conjugate minus t tilde, the Fourier transform of x2 conjugate minus t tilde is x2 conjugate f, that is f t of x2 or x2 conjugate minus t tilde equals x2 conjugate of f. And therefore, what we have over here, that is if x2t has Fourier transform f to x to f, then x2 conjugate or x2 conjugate minus t has Fourier transform x2 conjugate f. Therefore, now we can write the Fourier transform S1 to f. Remember, S1 to f is Fourier transform of your autocorrelation function R1 to tau, that is x1 of f times Fourier transform x2 conjugate of minus t or x2 conjugate of minus tau, which is basically x1 of f. This is the Fourier transform of x2 or conjugate of minus tau. This is the Fourier transform x1 of f times x2 product of the Fourier, that is x1 of f times x2 conjugate of f. Therefore, what we have is R12 of tau, which has Fourier transform S12 of f, which is equal to x1 of f times x2 conjugate of f. This is the property of Fourier transform of the Fourier transform of the cross correlation, this has to be the cross correlation. This is the Fourier transform of the cross correlation between two functions x1. This is a Fourier transform of the cross correlation, that is we are considering two different signals x1t and x2t. So, this is the property of the Fourier transform of the cross correlation, that is R12t denotes the cross correlation between x1t and x2t for a lag of tau. Okay. Now, what we are going to do is we are going to consider a special case of the cross correlation, that is the autocorrelation. Okay. So, now we are going to consider the autocorrelation which is basically now that is if I replace x2t by x1t itself, that is the degree of self similarity of the signal, that is characterize the degree of self similarity of the signal x1 t for a lag of tau, it becomes the autocorrelation. So, the autocorrelation is R11 of tau is the degree of self similarity of x1t x1 conjugate t minus tau. What is this? this measures the degree of self similarity, that is, this is the degree of self similarity of x1 t for a lag of tau, self similarity of x1 t for a lag of tau. So, therefore, R11 t from the property that we have shown before, simply we have simply replaced x1 t by x2 t by x1 t. So, this is the convolution of x1 tau with x1 conjugate of minus tau, that is your R11 of tau, that is the autocorrelation. This is the convolution operator. This is the convolution operator, and further if you look at the Fourier transform, that is S11 of f, that is Fourier transform of the autocorrelation is Fourier transform of x1 tau, which is x1 f times the product in the time domain, Fourier transform of x1 conjugate minus tau, which is nothing but, as we have shown previously, Fourier transform of x1 conjugate minus tau is x1 conjugate of f. So, we have x1 f into x1 conjugate of f. So, this is magnitude x1 f square. So, S 11 f, that is the Fourier transform of the autocorrelation of x1 t. This is the Fourier transform, and this is a very interesting property. This is Fourier transform of autocorrelation of x1 of t is Fourier transform of autocorrelation of x1 of t is magnitude x1 of f square, that is this autocorrelation, which is R11 of tau is magnitude x1 f square, where x1 f is the Fourier transform of x1 t, right. So, x1 t has Fourier transform x1 f, all right. Okay. So, this is important to keep in mind. So, what we have shown is a very interesting property, that is we looked at the autocorrelation function, all right, that is R11 tau, which characterizes the self similarity of the signal x1 t for a lag of tau. Its Fourier transform is nothing but the Fourier transform of magnitude square, magnitude x1 f square, where x1 f is the Fourier transform of x1 tau. All right. So, this is a very interesting property. Again, we are going to rely on these properties several times, that is the cross correlation between two signals x1 and x2 t, the Fourier transform, the cross correlation between x1 and x2, all right, x1 t and x2 t, and also the autocorrelation of the signal x1 t and the Fourier transform of the autocorrelation of x1 t. All right. So, we have looked at these concepts today, studied several properties, and we are going to rely on these properties in the analysis of different communication systems. Right. So, let us stop this module here, and we will continue with other aspects. Thank you.